Welcome to Climate Now. I'm your host, James Laure, and today we're speaking with Dr. Laure Zanna, a professor in mathematics and atmosphere and ocean science at the Courant Institute at New York University. Laure is the lead principal investigator for an international collaborative project named Multi-Scale Machine Learning in Coupled Earth System Modeling, which is abbreviated M-squared lines. Laure is joining us today to discuss how climate models work and the role that machine learning can play in improving their ability to make accurate climate projections. Laure, thanks so much for taking the time to speak with us.
Thanks for having me.
So I would like to set the stage for our conversation today by highlighting the importance of modeling in understanding what drives climate change. The Swedish Academy of Sciences recently announced the 2021 recipients for the Nobel Prize in Physics. Two awardees, Doctors Syukuro Manabe and Klaus Hasselmann, are IPCC authors recognized for developing physical models of the Earth's climate that accurately predicted global warming. Laure, can you tell us a little bit about what this means for the climate science community?
It's actually very exciting news. So 3 Nobel Prize in Physics. So 2 of them were awarded the prize for climate science, and it is very exciting for so many reasons. Obviously, seeing climate scientists being awarded a prize in physics is a great success, I guess, for climate science in general as a whole. Manabe was very much a pioneer in building kind of simple models of how the atmosphere will respond to climate change, and being able to actually make quantitative, if you want, prediction of what the atmosphere will do in response to climate change. He was also one of the key scientists who coupled an ocean model to an atmosphere model, so kind of the early version of climate models. The other one, Klaus Hasselmann, developed very simple models of climate variability. So basically, the weather hits the ocean is going to integrate that signal, and so that tells you how the ocean is going to respond to atmospheric noise. And he laid out a foundation to actually quantify or how to detect climate change in data. So, how the signal emerges from the noise.
Let's fast forward from the groundbreaking work that these Nobel laureates did to the state of the art today, which brings us to the work that you are doing with your project, M-squared lines. So this project is bringing together arguably 2 of the most talked about terms in the current popular scientific lexicon, namely climate science and machine learning. So to get us on the same page, can you define these terms for us and tell us why these fields can work together?
Machine learning is a type of artificial intelligence. So what it does, it allows, computer algorithm to make good and accurate predictions. As long as you have good data, and you don't need to actually tell the algorithm or program the algorithm to actually come up with those predictions. So that's kind of a perfect, data-driven methodology. If you have data, the algorithm can actually come up with good predictions.
And so just to make sure I'm following you, you're referring to algorithms that can quote unquote learn the patterns that are inherent in a training data set. When you feed them test data, which they haven't seen before, those trained algorithms can then pick up the same types of patterns as they learned from the training data. So you don't need to explicitly program to do this. Is that right?
Indeed, right? So we still need to learn something. And so to make those accurate predictions, we still need to give the algorithm some data. And then from that data, I'll be able to actually give us accurate predictions. So that's on one hand, the machine learning aspect of it. On the other hand, what is climate and what is climate change? So climate, we define it as an average of the atmospheric and oceanic condition at a given location over time. In kind of popular ways, it's like the average of the weather, right? So in 10 years, I can't tell you if it's going to rain in October 11th, but I can tell you on average if during that season it's going to be warmer or cooler, or if there's going to be more or less rainfall. But, the climate is an interaction between many phenomena on many different scales to get you to that picture of what the atmosphere or the oceans are going to look like. And so usually we describe the climate with its statistics, means or extreme of temperatures, or means or extreme in rainfall, the frequency of the events, the duration of the events. And so now let's try to bring those 2 together, right? So why machine learning would be useful, for climate change. And basically we can think about it as a tool to actually understand or predict climate change. So if you give the algorithm data that we can measure or that we can simulate, then can the machine learning algorithm uncover relationship between, say, temperatures and floods, or flood levels and storm intensity. And so really getting the algorithm to actually learn from the data and basically come up with better relationships and better prediction.
Got it. And so as I understand it, and I'm by no means a machine learning expert, for machine learning methods to be successful, you have to have fairly extensive training data on which to train the algorithm, and then you have to have some data set on which to test the algorithm and then derive how well it's able to make these predictions. So what's a good example of some training data that we've trained models on that then we know have been trained successfully because we've tested against robust and unlinked test data set?
So one approach that we really like to use is simulated data. So, you basically try to simulate, say, pieces of the oceans or the atmosphere. And so you can run your simulation, you save as much data as you want, and then you split the data sets. Say you're going to use the data that you run in the simulation when the present day climate, say, and so you're going to give your algorithm a lot of data from that simulated present day climate. You're going to train the algorithm, come up with a relationship or a prediction. Then you're going to test it in a different simulation. But now, say, the carbon dioxide levels are actually higher. So, you didn't give the algorithm that data set anymore because it didn't see a higher level CO2. And so you can test it on that new data set. And that's a way to actually decide if your algorithm actually learns something that might be robust in a different climate. So simulated data is a nice way to go around this because you can actually go and rerun your simulations under different conditions and test it against.
Would we ever use actual measured data? Because we have a lot of temperature data and we have a lot of weather data.
It's a great question. So for certain aspect of using machine learning for climate, it is being done. So people are training the simulations on observed data to try to make predictions. It's a harder problem, right? Because you need a lot of data and it depends on how far you want to make your predictions. So there are models currently being trained on observed data to make short-term forecasts.
Interesting. Because it would seem, and tell me what's wrong with this. So if you're using a simulated data and you're training your algorithm based on that and you're asking it to make predictions, wouldn't it just be learning the characteristics of your model, right? It's not really learning something about the world, or is that wrong?
All right. And yes, absolutely. A model is only a description of the world based on physical laws, but they are imperfect. And so that has been a big question for us on how to make those models more accurate. But you're absolutely correct. When we learn from simulated data, there's a little bit of learning some of the errors also associated with that model. When you learn from real observations, you usually are limited by either the accuracy of your measurement or the fact they're sparse, meaning that you don't have temperature at every single location at every single time point if you want. So we live in this kind of imperfect world where observations are the best thing we have, but are incomplete. Model data is a pretty good representation of the world, but it's still an imperfect representation of that world.
And so to make sure I'm understanding this properly, the end goal of applying these machine learning methods to climate would be to derive real predictions about the actual physical world, right?
Correct, yes. And there are different routes that one can take. You can either, decide to train your machine learning algorithm just on data and make a prediction. Say, just basically data-driven, no physics, pure let's learn relationship and see if I'm going to predict what weather or the climate might be over the next season or the next year or the next decade. And so that means here now you completely forgot the physics, right? And so you're going at it by just making a prediction or learning a relationship. That there's one part where we know the physics and we're going to have an add-on, which that add-on is just going to come from the data part. And so it's a bit of a hybrid between the model world where you have good equations for it, but they're still imperfect. And then you supplement them by something that you learn from data. So that's kind of a little bit of the hybrid world of it.
Okay, so I'd like to focus in a little more on climate models. Can you tell us about how they work and what the motivation is behind applying machine learning techniques to these models?
First, what are climate models? Right? So what we're doing is we're taking, the laws of physics, whether it's the fluid dynamics, the thermodynamics aspect. They are the best description we have of what the climate is, how it will evolve in the future. And so climate models are a way to quantify what will happen, what's happening now, what will happen in 1 year, 5 years, 10 years, and so on. They've been doing an outstanding job at predicting warmings in the ocean and atmosphere, or at least on average, but they can differ in their prediction, right?
Right. So then how do we assess which model makes the best projections? For example, can we compare what the models project to what's actually happening in terms of current measured temperature and other climate data?
Yes. So usually that's the way people evaluate climate models all the time. So you're going to basically compare, say, surface temperatures or precipitation to the current observations. So usually you're going to basically draw a map of, say, the average temperature that we have measured in the world over 50 years. So you're going to end up with a given map of that average temperature. You're going to do the same for your climate model. Then you're going to take the difference between the two. Then, of course, do a little bit of a quantification of error. So it's kind of interesting. Some regions end up with 2 degrees Celsius difference between the model and the observation. That's pretty big, right, at a given location. On average, some models will end up with an error that can be 0.5 degrees Celsius. And so, again, they are the best we have, but they could be more accurate. So one way they could be more accurate is if you were having more computational power. So that would be one, but we're limited by computing power. So usually there are processes in those climate models for which we basically don't have enough resolution or computing power to actually solve. And that can be, how temperature or heat is being mixed in the oceans and atmosphere, or how clouds will respond to a changing climate. So those processes and how they impact the large scale are not accurately represented right now. And so what we're trying to do in M²Line is say, okay, let's actually start using data and machine learning to learn those relationships that are not well captured in the climate model we have. So we're going to keep our laws of physics and we're going to continue solving them the way we have, but we're going to supplement them. We're going to come up with better relationship between, say, mixing and temperature in the oceans or the atmosphere, or how clouds will respond to different temperature, using machine learning data and couple that with the current climate model we have.
Right. So essentially, we know that the laws of physics are behind the changes we're seeing in the climate, but these laws are operating on all kinds of scales in all kinds of physical processes on Earth, whether it's, as you mentioned, the mixing of heat in the oceans to the evaporation of water from the seas to the coalescing of clouds. And all of these things are playing some role. But your point is that it would take an amount of computing power that we don't have and will never have in order to solve every equation. So we use the methods in machine learning to derive just the relationships that we don't understand then at the level of the microscopic.
Yeah, that's very much the essence of it. Is like, can we actually learn relationship from data of those processes that we've been lacking in understanding, and couple them with the climate simulators that we have today. And so M²Line is very much this kind of blend of theory, data, machine learning merged together to improve climate models.
Interesting. Wow. And so what are the model input variables that you're working to improve more specifically?
So, as we just said, right, we have the laws of physics, then we need to solve them on the computer. So we have to divide the climate system in boxes, or what we call grid cells usually. And so we're trying to mimic how the ocean, the atmosphere, the ice will evolve and interact with one another. So currently, the grid of climate models is about 50 to 100 kilometers horizontal resolution, right? So you have boxes that are about 50 kilometer by 50 kilometer or 100 kilometer by 100 kilometer. Those boxes are tiling the Earth both horizontally, but then in height in the atmosphere or depth in the ocean, right? So you're going to have a lot of stacked layers both in the oceans and atmosphere. And so anything that is happening below that scale, right? So below 100 kilometer or 50 kilometer is actually just not captured. So it's not represented. So anything that is below that scale is actually not resolved by the climate simulators.
Yeah, the proverbial butterfly that's flapping its wings in Central Park is not captured.
Definitely not. The small sensitivity to initial condition will definitely be part of it. But of course, for the climate, we're really looking at the long-term statistics. But truly, as you were alluding to, anything that is small scale that is happening below that grid box is slowly going to impact the larger scale and the longer time scale. And so that's why it's very important. So, again, we can go back, to mixing in the ocean. So putting CO2 into the atmosphere, we're warming the atmosphere. More than 90% of that excess energy that we're putting in the climate system ends up in the ocean. So the ocean is going to take up that heat, but then it's going to start mixing it and steering it. But it's happening at a scale that is much smaller than the grid box size of the climate model we have. So we need to come up with a relationship to actually mimic that mixing or that steering in the ocean. So far we've been doing it using empirical physical relationships, and it got us so far. And so now the question is, can we actually use data and machine learning to actually represent those processes? So to go back to your question, so which processes are we trying to tackle? So ocean mixing and turbulence, atmospheric clouds and convection, all those processes are pieces that we're trying to do a better job at. And now, what would they impact on the large scale? So again, the rate at which the ocean takes up heat, how much precipitation you will get in a given region, how extreme temperatures over the US will change. So all those phenomena will affect both the local and the global scales as we think about predictions over the next few years, if not decades.
So I wonder if you could, just to paint a picture for our listeners, what is actually happening when we model the climate? Are we talking about a huge center full of supercomputers that is staffed by 100 scientists, or is this sort of a very distributed model somehow?
I mean, we can start with where climate model development happens. So usually it's centers that are basically a large team of scientists, model developers, software engineers, really trying to actually make those connections from the theory all the way to actually running those big simulations. So as you mentioned, you're going to run that on supercomputing, which are usually located somewhere in the US, not necessarily at the same place where the model developers are, but this is usually the way we think about this. Now, people at universities in general can contribute to the theories and to the understanding and the model evaluation and so on and so forth. But the big efforts are usually concentrated in those modeling centers. And now different centers have different philosophies, right? So some modeling centers try to develop models that might be used both for weather and climate. So say trying to predict the weather over the next 10 days and also trying to predict the climate over the next few decades. Others are building models that are more user-friendly. Say you want to strip down your model to something that is just the ocean with no land, or you want to add another component, or you want to run it in a configuration that is different, then you can. So there are different philosophies for different modeling centers. But usually this is not a small enterprise. This really requires thousands of people really committed all the way from theory to something that is optimizable on a supercomputer.
And what are the sort of primary models in use today?
So that's, again, going to depend a little bit on what application you have. If we consider just, say, climate projections, so there are quite a few. In M² lines, we're actually trying to tackle 3 different climate models. One of them is based at GFDL, so again in Princeton. Another one is being developed at NCAR, which is in Boulder. And a third one is in France, IPSL. So those are 3 of the leading models used for climate projections in general. There are many others, right? There are dozens of models nowadays. Many models help you capture a little bit better the uncertainty associated with the different processes that we can't represent.
I see. So what is the setup for M² lines, and how far along are you with that project?
So we are about 30 scientists now, 9 institutions, including 3 modeling centers. And so we have expertise, from atmosphere, ocean, ice dynamics, to machine learning, to climate model development, right? We have model developers on the team. And that's very important to actually get that depth and breadth as well, to actually be able to make that step. So the project started a few months ago now. We had a lot of preliminary work to actually test how machine learning would be useful to actually represent some of those processes like convection in the atmosphere, ocean mixing, and so on. And so the main impact that we're trying to get to is really improving climate models, especially the surface temperatures, both in the oceans and the atmosphere. And so why that? There's a big reason is, of course, everything that is happening at the surface is the interaction between the different components, the ocean, the ice, the atmosphere. And so as we described earlier, we put CO2 into the atmosphere, we warm the planet, then this is communicated to the ocean. And so all of that is done at the interface. Or we're melting the ice because the planet is warming more. So our first goal is actually trying to improve what's happening at the surface of those coupled climate models. So that's our big benchmark here, because it has an influence on pretty much everything. Rainfall, ocean warming, ice melt, and so on. We are going forward with what we call the implementation, meaning the coupling of those new relationships we learn from data with current versions of climate model over the next 2 years. And so that will be some of the few test cases for ocean mixing in particular and convection in the atmosphere. And slowly kind of moving towards a broader range of processes, especially at the ocean ice interfaces and other processes deep into the ocean and up into the atmosphere. And so that will actually slowly get built towards the end of the project.
Got it. So in terms of actually knowing if the contribution of M squared lines improves the model, will you know this because the model does a better job predicting real data? Or if not, then how will you know if these contributions actually improve the model?
Yeah, so that's a great question. So as mentioned, so what we're trying to improve is how the model will simulate the current observations, basically. Would it give us a better representation of surface temperature, both in the oceans and atmosphere and other large scale quantities that we can compare with current observations, real measured, observations of the real world. So that's step number one. So that's how we know that we built a better climate model. Now, we want to have better predictions, right? Now, I can't tell now if I did a good job for my predictions in 5 years. I'll know in 5 years. But what we can do is try to build better uncertainty quantification with those representation based on data that we're learning. So that gives us a better confidence in our prediction. But the first baseline, you're absolutely right, is actually trying to simulate observed data in surface temperature, both oceans and atmosphere, to tell us if we actually built better climate models.
Got it. And so you described before this tiling of the Earth, meaning sort of these 100 or 50 square kilometer or 50 kilometer cube boxes that are covering the
tiles,
Earth.
Yeah, the depth can actually be quite different.
Oh, okay.
Believe it or not, yes.
I see. Okay.
So the horizontal direction, they're 50 kilometer by 50 kilometer.
I see. Okay. So
the third dimension can be widely different.
Can be widely different depending on the altitude?
Exactly. Yes.
Okay.
Yeah, absolutely.
So if we're trying to then assess the effectiveness of the model, how many sensors are there out there? I mean, do we actually have a sensor at every 50 square kilometers on Earth? And how do we actually look? No. Yeah.
Correct. Yeah. I think, kind of go back a little bit to some of the earlier questions, right? Which is the data is sparse in terms of the real world, and we don't have observations everywhere. So in the recent years, there's been really kind of a revolution in terms of the amount of observations we have. So I'll take again, because we've been talking about, the surface of the planet. Satellite altimetries have really kind of revolutionized the way we actually see the oceans, for example, the surface of the planet. So we can get pretty good measurements at the surface of the oceans for, say, temperature or sea level, the ups and downs at the surface of the oceans, for example. And that has a resolution of about 50 kilometers or so. So you can get a bit of a picture of that. Now, of course, that's at the surface. Below the surface, then that gets a little bit sparser. So we have floats that can dive up and down and kind of gives you measurements down to 2 kilometers in the ocean. They're called algo floats. And so they're pretty cool and fancy, but below 2 kilometer depth, then there's still 3 kilometers of ocean on average. We don't have a lot of measurements there. So we always have this kind of problem, right? Do we have enough data? So usually what we do to actually assess our models is we look at the average, over many years, say, over large scales. Or we look at the probabilities of, say, temperature over a large region and see if the model actually captures roughly that probability. But that's true, evaluation with real observation is not a simple task.
Right. Because I suppose you can assume that if it's capturing probabilities correctly, if it's capturing averages correctly, then it knows something about the underlying process, and it's probably correct, because otherwise how would it know? Right.
Exactly. So and you want to have many of those metrics to test, not just one, because yes, it might be a little bit of luck. So you want to try to capture as many as you possibly can based on the observations you have. So then, you have a set of metrics, and the more of them the models get right, the more confident you have that the model is more accurate. And of course, the more trust you have in the projections you're going to make, so that the end user, whether it's just scientists or whether it's governments or end user who are actually trying to make decisions for adaptations or building infrastructures in the city, can actually trust the predictions over the next few years.
Right.
But this is definitely an exciting area of research, obviously. I mean, not just only for going after those processes and trying to understand them, but really trying to build tools that are useful not just for scientists, but for the community at large.
That's it for this episode of the Climate Now podcast. You can check out our other interviews, watch our videos, and sign up for our newsletter at climatenow.com. And if you'd like to get in touch with us, email us at contact@climatenow.com or tweet us at WeAreClimateNow. We hope you'll join us for our next conversation.